Hi there and welcome back. Let us look at this amazing example over here. We are going to react ethylene with water to form ethanol. Okay, let's do step by step using Aspen Hysis. First step is to add our components. I'm going to add my ethylene, water, and ethanol. The next step will be to add our thermodynamic properties. I decided to go along with Peng Robinson. It's important to do your research and choose the most desired thermodynamic property. If you click on next, Aspen is going to ask you, do you want to calculate everything, the properties more especially? Just say yes, and let's move on to the next step, which is the simulation. For our simulation, I'm going to have two inlet streams, that is our ethylene and water. Now, ethylene and water are almost opposites when it comes to these thermodynamic properties. For example, ethylene at room temperature, it is a gas, meaning it's in its vapor form, else water at room temperature, it is a liquid. Also the opposite. For example, if ethylene now it's a liquid and that's below -degrees Celsius, water is ice at that point. So the most desirable or favorable condition that these two can relate at, it's at gas phase. Let us feed our water at 25 degrees Celsius, which is liquid phase, and then heat it up to just above its boiling point, and that's above 100 degrees. I decided to go with 150. Whereas for ethylene, let us feed it at room temperature, and at that state it already exists in its gaseous form. Allow the two streams to mix in our mixer, and once you have solved everything and there's no errors, the next step now will be for us to add our reactor. For the reactor, I decided to go along with the Gibbs reactor. You could have selected any reactor of your choice. It's always interesting to try different reactors and how they operate or affect your simulation, or the conditions and the parameters, or the results rather. So for this example, let's just go along with the Gibbs reactor. For the Gibbs reactor, I am going to play around with our temperatures. Initially, I said let us react water and our ethylene at 80 degrees, and I got a very low formation of our ethanol. I lowered the temperature to 58 and ethanol began to pick up. I increased the pressure as well. Formation of ethanol also started to pick up as well. I could see that the mole fraction was now becoming to increase at least 80%, so that's where I left it at 81%. So yeah, play around with your numbers there. You'll notice that pressure also does have an effect. The next step is to add our separator now. You'll notice that Aspen is different from DWSim. I also did the very same example on DWSim. Please check it out. On DWSim, you have to use your brain and think a lot. You have to think of the number of stages, the feed stage, the temperature and pressure within your column. Whereas here on Aspen, you just define your outlet stream. I decided to just specify that for the bottom stream. So I said I want 100%. I just told Aspen and it did that for me. Consequently, it calculated my top outlet stream as well, which was 100% water. So there you go, ladies and gentlemen. I hope this example was easy and understandable for you. Hi there and welcome back. Let us produce ammonium using nitrogen and hydrogen. We are going to use Aspen Hysis for the entire simulation. Okay, let's start. So for the first step, it is to add the components, which is our hydrogen, nitrogen, ammonia, methane, argon, and carbon monoxide. The next step will be to go under methods. For methods, we are going to add our property package, and we are going to search for our KS, which is basically HYDRGOREN equation. If I'm unable to pronounce it, forgive me. Now our next step under parameters, still under methods. Now we are going to go under binary interactions. Click on the RKSKBV-1 if it does not generate a tick automatically. Else you can just click next, which is just at the top. Next step is to move to the simulation. Let us open a flow sheet and add our equipment accordingly. So we are going to use a compressor, a mixer, a heater, one stoichiometric reactor, second heater, and also a flash column. Also add your streamlines and title them accordingly. So the inlet stream 1 can be the feed. The outlet stream of the flash column, we will have some few unwanted byproducts exiting at the top, which can also be purged and some of them recycled back into the system that we need. But for this tutorial, I did not add the recycle stream. We can also have the outlet stream exiting the flash column number 2. At the bottom, we can label stream 8 and rename it to ammonia. Now let's edit the first stream. The first stream, which being the feed, total flow rate that we'll have there, it's 1,500 kilomoles per hour. Specify your inlet flow rates as they are entering accordingly. Next step, let's edit our compressor. Let it be isentropic at 271 atmospheric discharge pressure. No need to edit your mixer, just ensure that everything there is accordingly. For example, the pressure at 0. Valid phase, there we have a vapor liquid. Maximum alterations and error tolerance, you can just leave it like that. Let's edit our first heater. We are going to specify the temperature and the pressure. Now edit the stoichiometry reactor specifications and add the reaction with the fraction conversion of nitrogen being 40%. Remember the balanced chemical reaction for ammonia is 3 hydrogen molecules entering, only 1 molecule of nitrogen entering to produce 2 molecules of ammonia. Kindly note also the reactants will be negative whilst your products being positive. Next will be to edit the second heater with the temperature now being at a 300 Kelvin, pressure still being 0 atmospheric pressure. Lastly, let's edit our flash column. The type there, we are going to specify the duty and the pressure. Once you're done, run your file. Initially, I got an error because there was one stream that was not connected. I just reconnected the destination of the stream, and after solving it, we managed to get our results. Now let's look at our results. If we look at our results, I understand my results more. It makes more sense if I look at it in form of moles. Multiply by 100 to give us percentages. So we have the mole fractions of our nitrogen and hydrogen entering to produce 97% ammonia. So that is a great conversion that we have over there. You can manipulate your temperatures if you wanted to get or achieve 100% ammonia, but for now we ended up at 97. Let us produce pure butane from natural gas using Aspen Hysis. Let us start. I've opened my simulation. I'm creating a new simulation here. Let's add our components under properties. We are going to add nitrogen, carbon monoxide, methane, ethane, propane, isobutane, and butane. The next step is to select a property package. In this scenario, we are going to work with Pang-Robinson. You can simply click on methods or just next. We are done under properties. Now let's move to the simulation. Under the simulation section, it will open a new flow sheet, which will be our main flow sheet. We can add all different components that we want to work with. So we can add our separator, heater, cooler, second separator, mixer, and also the last or third separator. We can also specify the streams that are going into and out of our equipment. So we are going to have a feed stream. We'll have 2 streams exiting from the separator, the top stream being the vapor and the bottom stream being the liquid. The streams will be connected respectively. Also, labeling the streams can make it easier when it comes to just for point of reference, as well as also labeling our equipment accordingly. There is no strict rule on how you should label. You can label per preference. The next step will be to edit our feed stream. For our feed stream, we are going to feed natural gas consisting of 0.01 mole fraction of nitrogen, 0.01 mole fraction of carbon dioxide, methane being at 0.6. We have ethane at 0.2, propane at 0.1, our isobutane at 0.04, and butane at 0.04 as well. After editing our feed stream, we can continue now, proceed by editing the first separator. For the first separator, we are going to specify only 1 outlet stream, at least that's what Aspen requests from us. For the heater, let us specify the temperature to be at 14.85 degrees Celsius or 288 K, and also our pressure there being at 0.68 atmospheric pressure, which is roughly converted to 0.68901 bar. Next, let us Now edit the cooling section. Using the similar equipment, this time around our heat exchanger will act as a cooler because we'll specify it in terms of temperatures. For our mixer, we really don't have to do a lot. Not much needs to be edited there. Let's proceed to our final separator, the last separator. For this separator, we are going to specify the final outlet stream that we choose to obtain. Our wish is to obtain pure butane at least 100%. For example, we can get isobutane at 0.45 and butane at 0.54. If you add those together, including the decimals, it should round up to 100%. Now Aspen will tell you at the bottom on your left corner, you've added all the required basic minimum requirements, and now it is ready to run this file for you. If you're happy, you can run this file and your answers should tabulate. Without analyzing our results into detail, but just looking at our mole fractions, we can see there that we did manage to obtain 100% of butane in our product stream without much of the errors. Feel free to simulate yourself as well, look at the report that you generate and analyze your results. Thank you so much for watching. I really hope this was helpful. Till next time, bye. Let us look at this example here. This will be divided into multiple series whereby we are going to look at the simulation as an entirety, as a whole. We are going to explore the reactor design, how to get the volume and how to size your reactor using 3 different methods to get your volume. We are also going to use the ODE solver such as Octave to help us solve and integrate some of those long equations. The next thing we're also going to do is also do the heat exchanger design. So we are going to look at multiple things here. I'm going to separate this into at least 3 videos so that you can and get the concept or the ideology behind this entire project that was designed over here. As you can see on my screen, we have a simulation here, which is basically the production of ammonia from hydrogen by mixing it with nitrogen, and our hydrogen is super green as it is produced from water. I always feel like it's important to mention that there are various ways. There's multiple ways to make and produce hydrogen. We could have probably just decided to say we are going to use the combustion of glucose in the presence of oxygen and water to form carbon dioxide, and hydrogen. We could have also said we are going to use Dimethyl reforming, where we are going to react methane and water to produce carbon monoxide and hydrogen. We could have also reacted our methane with carbon dioxide, produce carbon dioxide and hydrogen. We could have separated ammonia into nitrogen and hydrogen. So basically there's multiple ways, guys. We'll take a shift reaction where we react carbon dioxide and water. So there's really many ways to produce hydrogen. But for the sake of this project here, let us say we want to produce a green hydrogen, as green as possible. So we are going to use water electrolysis. The first step, when you go to your Aspen simulator, if you have it, if you have Cocoa, you can use Cocoa. If you have DWSim, use your simulator of choice. I will really try my best to simulate this with more than one simulator. For the first example, it's just an overview of the Aspen simulator. I'll do a detailed one for Cocoa and DWSim. So if you go to properties, you are going to have to add your components. Now for this particular example here, we are going to have water, hydrogen, oxygen, nitrogen, potassium hydroxide, hydroxide ion, and ammonia. Once you've added your components, we are going to make use of a tool called Electrolysis, which goes hand in hand for a simulator on Aspen, which is meant to be designed for water electrolysis. Another thing to consider, it's the methodology, still under properties. Which method are we going to use here? Let's say we're going to use a base method of electrolysis. Now that we've looked at the basics, let us go to our simulator. For our simulator, you can see it as at its entirety. It's very straightforward, pretty simple. Nothing complicated over here. Okay, let's look at it. To produce hydrogen stream 8, we have to react stream 1, which is water and its electrolyte solution, together with stream 2, which is pure water. These two can be mixed at 1 bar and ambient temperature of 25 degrees Celsius. After they've mixed together, they will form a stream number 3. We are going to pump everything here to our heat exchanger. Now, the purpose of the heat exchanger in this simulation here is to ensure that we increase the temperature from 26 degrees Celsius to 90 degrees Celsius. After our reaction takes place, we can therefore then separate our water into hydrogen and oxygen. Now this stream will be fed into reactor 1. This reactor here will act as our electrolyzer, and we will be separating our water into hydrogen and oxygen. Now stream 6 will then further move to the separator. After it moves to the separator, we now have to separate our resulting stream of 6 into hydrogen and pure oxygen. You will notice that there will be some few small traces of hydrogen in stream 7, as well as some small fraction as well of some water vapor. So our oxygen is not pure, it's 86% oxygen and a few traces of hydrogen and water. Now this oxygen here, to be prevented from being sent into the atmosphere and causing some further damages, we can therefore decide to sell it to separate industries that make use of this oxygen into their process simulations. But for us, because we don't need it as a byproduct, we'll be selling it and just solely focusing on hydrogen that was produced. The produced hydrogen will therefore further move into the mixer. Mixer 2 has 2 inlet streams, which is hydrogen and pure nitrogen. Our nitrogen is pure, does not have any other impurities such as argon or any other traces of what we don't want. These two will mix together and will form stream 10. Still at 1 bar, but the temperature is slightly higher at 74. Because we want to increase the pressure, we are now therefore going to move everything through a compressor to increase the pressure from 1 bar to 200 bar. Also, the temperature drastically increased in this scenario. Everything now flows to mixer 3. Mixer 3 has 2 inlet streams. One of them is actually the mixed nitrogen and hydrogen. At high temperatures and pressures still, a second heat exchanger is used just to slightly increase the temperature from 300 to 500. Now, this was determined to be favorable for our Haber-Bosch process, which is whereby we react nitrogen and hydrogen together to form ammonia. The reaction takes place inside of our second reactor here. After the reaction takes place, we'll see some few traces of ammonia, nitrogen, and hydrogen forming from our product reactor stream, which is 15. The aim is now to reduce the temperatures. We will therefore use this heat exchanger here, heat exchanger 3. This heat exchanger is used to reduce the temperature. One can also introduce another heat exchanger, actually, introduce the fourth heat exchanger into this process simulation to further reduce the temperature of ammonia, because ammonia is liquid at lower temperatures. The stream then moves to the separator, whereby we achieve 99% conversion of ammonia, and we can recycle some few byproducts that we don't want in our ammonia stream, such as nitrogen and hydrogen, to go back and re-react. Hence we have mixer 3 with an inlet stream of 12, which mixes together with stream 11. I hope that makes sense. The next step now is to do a detailed design of our heat exchanger HET3, and also a detailed design of our reactor, the RECT, the second one. On today's lesson or tutorial over here, we are simply going to look at the production of hydrogen from water electrolysis. This is considered a green hydrogen because we are using a renewable source like water. Now to start, I'm going to use my Aspen simulator. I am going to go under components, add water, hydrogen and oxygen, also potassium hydroxide. The next step now will be to select Electrolysis, and it's there to aid with the computing of water electrolysis. Once your Electrolysis has opened up, you will see some various options there. It will first introduce you to Electrolysis. The next step for us will just simply be selecting next. After selecting next, it will give you various options that you can select over there. We are going to specify that in our electrolyzer we are going to have water, which is H2O, and potassium hydroxide. Once you've done that, you are going to select next. Once you're satisfied with everything, now you can close your electrolyzer. The next step now will be for us to go to the methods. Under methods, we are going to select the base method of electrolyzer. Select next until the file or the simulation runs, and once everything has been computed, meaning it has processed all the data that it has received, now we can start with our simulation. For our simulation, we have 2 streams that are inlets. The first stream will be water and an electrolyte solution of potassium hydroxide with a fraction of 0.8 and 0.2. The next step now will be to have pure water just entering our stream at 100%. These two will mix at ambient conditions, which is 25 degrees Celsius and 1 bar. After they've mixed together, together, we are going to form mixer stream outlet number 3. This stream's temperature is pretty low. It's at 26 degrees Celsius. To increase it to 80 or roughly 93, you can use a heater, a heat exchanger. We are going to specify the temperature of our outlet stream. In this scenario, it will be 93 degrees Celsius. Now we can introduce a reactor. In this scenario here, we selected the stoichiometric reactor. What's going to happen here is that we are going to have to specify the stoichiometry of our reaction. So you have to specify the balanced equation. So we are going to enter there that water, which is the reactant, is going to separate into hydrogen and oxygen. In this case, since water it's the reactant, it will have the minus sign, and the products will have the positive sign. I did make a mistake there. I wrote 1:1, where else that was wrong. I was supposed to write the balanced chemical reaction, hence I had to go back and fix my equation. After solving and you are happy with everything, the last step now is to have a separator. By the way, the reactor acted as the electrolyzer, hence now we are separating the products that were formed after water separated into its constituents. For the separator, we are going to specify that the top stream, which is stream 6, is going to have 100% hydrogen. For Aspen simulator, that's all you have to do, versus with other simulators like DWSim and Coco, you might have to impute more information like the temperatures and pressures. But here, all we have to do is just to specify the outlet stream. So we said here we want 100% conversion of hydrogen. Because hydrogen is hard to handle, we are going to decide to store this hydrogen in a form of ammonia. So we have to react it with nitrogen. I'm not going to show this here on the simulation, but there will be various simulations that will come up after this particular upload. Stream 7 can now be recycled back into our system because it still has a lot of water, or I might have to control some of my parameters there, such as temperature and pressures. The aim was actually to achieve a higher conversion of oxygen. This was a very straightforward example. I was just giving you an idea of if you wanted to use an electrolyzer on Aspen, how you'd go about it. Feel free to ask more questions. If you want more videos, I'm definitely here for you. Till next time, bye. Hi there and welcome back. Let us look at a kinetic reactor using Aspen Hysis. Let's say we are working with a simple equation here whereby we are reacting nitrogen, hydrogen to form ammonia. So I'm first going to start under properties by specifying my components. Next is to now specify our method, and we can say we are going to be using the Pang-Robinson. Now let's go to the simulation itself. We have there a flow diagram whereby we have an inlet stream, our plug flow reactor, and the outlet stream. For the inlet stream, we can specify the conditions such as the temperature and the pressure. We can say we are feeding at 250 degrees Celsius and 150 bar. We can also specify the molar flow rate that's flowing in. Now let's look at our reactor. For the reactor, we are going to say it's an adiabatic reactor. The configurations there, we can say we have at least 40 number of tubes. The reactor length there, it's 4.88 meters, and the diameter is 0.025 meters. For our reaction inside of our reactor, we are going to write there the stoichiometric reaction of our balanced equation, whereby the reactants are negative and the product will be positive. In terms of kinetics, this information you can get from literature. Specifically for my ammonia synthesis, this is what I got. The first term there, it's for my forward reaction, and for the second term, it's the reverse reaction. I also specified the coefficients of each reaction. Lastly, we can also specify our adsorption term. Once you've done everything under your reaction kinetics, the next step now is to look at our catalyst. We can specify and say yes, we are going to have a catalyst within our system with a voidage of 0.33 and also a density of 1200 kilograms per meter cubed. After you react everything, you should get your results on Aspen Hysis. There was some conversion there for me, but I wasn't entirely happy. As you can see in my feed stream, there was 0 ammonia, but after the reaction took place with the aid of a catalyst, we had some ammonia starting to form within our product stream. Lastly, we can also analyze our profile, and what it helps us is that at every reactor length, we specify that our reactor will be 4.88. It will show you different parameters such as the residence time, or the time it takes for a reaction to take place. We can also look into our residence time there. As you can see there, our reaction really does take place really quickly, super fast, in terms of hours and seconds. So yes, this was just the basic knowledge on how you can use your Aspen on how to design a kinetic reactor. Obviously, you can modify this, but I was just giving you guys the basics. I hope this helps. Till next time, bye. Let's look at this Aspen simulation here of ammonia reactor design. So this particular simulation was already done on my YouTube video, on my YouTube channel. We've already uploaded on it, we've talked about it, and I promised to give you guys a detailed reactor design for reactor number 2, right? That we are going to look into and explore together. This is a very beautiful, straightforward, detailed simulation that you can check out for yourself. But for the sake of this example, I'm solely going to focus on one equipment, and that is this equipment over here, which is reactor number 2. There's already information available for you on my YouTube channel in terms of how to simulate everything. For the first video here, we basically looked at a detailed example of ammonia reacting hydrogen nitrogen that was produced from basically the water electrolysis that was produced here. Once you've checked out both the simulations together, you can now look at the final simulation here, which is basically a combination of these two, simulation 1 and simulation 2. We are going to be designing our reactor. There's some information that I might be leaving out here, like the kinetics of our reactor. That one I feel like is important to do research in terms of literature, what kind of catalyst is used, and the catalytic information that can be received or obtained. So let us say that we are dealing with a plug flow reactor over here, and our plug flow reactor happens to be adiabatic, meaning there's multiple tubes inside of a reactor, as there will be some heat loss. If our heat exchanger was isothermal, there wouldn't be a need to have multiple tubes. We can just have one large big tube inside of a reactor. So there's 3 equations that are there that I found. The first option there takes into account the volume of a catalyst for one tube of your reactor. If we multiply that one tube by the number of tubes inside of a reactor, you can get an estimate, a rough one, of your entire volume of the reactor. The second equation there takes into account the plug flow reactor equation in order to design the volume of your reactor. And lastly, the third option there is the equation that I also found here. It helps you to calculate the volume of your entire reactor. So let's look at every one of equation that you are looking at here on my screen. Option 1, we are going to be sizing the reactor using this equation here, multiply the number of tubes to get the entire reactor volume. We are going to derive 3 expressions. These 3 expressions, once they are solved simultaneously, they can help us calculate the volume of the catalytic reactor for one tube. The first equation is in the form of catalytic weight. The second equation, it's basically the pressure drop inside of our reactor. And lastly, the third equation takes into account the temperature change inside of our plug flow reactor. We will be reacting nitrogen and hydrogen to form ammonia. Let us let nitrogen be expressed in the form of species A. Let us let hydrogen be expressed in the form of species B, and ammonia be expressed in the form of species C. Now, the rate law expression can also be expressed in the form of partial pressures. We'll get into it just in a minute. We can also express now the material balance of our entire plug flow system in a form of molar flow balance, which is F, and its units is basically mole over time. We know for a plug flow reactor that the rate law expression can be expressed in the form of the inlet species A flow rate multiplied by the conversion, which is X, divided by the change in volume. And the units for this particular rate law expression here, it's mole per time and volume. So if we make V subject of the formula here, we will get FAO expressed in the form of conversion and rate law. We can express our rate law expression in the form of partial pressures, with A being species A, B being species B, and C being species C, respectively nitrogen, hydrogen, and ammonia. We can therefore now relate the partial pressures in the form of its mole fraction multiplied by the total pressure. This can be expressed for species A, species B, and species C, respectively. We can also now further express our molar fraction YA in a form of FA and FT. So this simply means here that fractions YA can be expressed in the form of FAFT, which is the flow rate FA that's in the product stream divided by the total flow rate that's going out of species A, B, and C. We can do this now, express Y in the form of species A, B, and C. Hence we have YA, YB, and YC. We can now therefore look into this equation here, which basically say the molar flow rate at which A leaves the system is basically equal to the molar flow rate at which A is fed into the system minus the molar fluid at which A is consumed within the system, and this is expressed using this equation over here. We've derived everything in the form of conversion. We can express our Ft in a form of conversion as well, which leads us to molar fraction of A also being expressed in a form of conversion. Because remember we said Ya is equals to Fa over Ft. Now we know that Fa can be expressed in the form of its conversion. Ft can be expressed also in the form of its conversion. We can do this respectively for Yb and Yc as well. We said the rate law can be expressed in a form of partial pressures. We've derived Pa in the form of Ya and P, so we can substitute, and we've also derived Pb in the form of Yb and P. We can also further substitute now Ya, because it was expressed in the form of Fa and Ft, and Yb can be expressed in the form of Fb and Ft. We know that Fa can be expressed in the form of conversion, and also Ft can be expressed in the form of conversion. So you can do this for B as well. We know that this expression here, it shows us the rate law in the form of catalytic weight, FAO, and change in conversion. We can make catalytic weight subject of the formula and substitute Ra into this equation here. It will yield this final equation here, which we can call equation 1. Because this reaction takes place in a gas phase, pressure drop cannot be neglected. So now we are basically going to substitute everything into this equation here. PR basically expressing the ratio of the total pressure of the product stream versus the inlet pressure of the feed stream. This A here, it is said to be a constant that is used in this equation and basically expresses this expression over here. With B also being a constant that depends on the bed of the properties of our fluid. We can also expand B, whereby it's expressed in the form of superficial mass velocity. It's also expressed in the form of the initial gas density, the diameter of the catalyst of the particle, and also viscosity. If we substitute A and B, which are both constant, into our pressure equation, it will yield us equation number 2. Lastly, because our reactor is adiabatic, we cannot neglect the change in temperature because it won't remain constant. If it was isothermal, we could have neglected the change in temperature just to be 1. But now, because there is a change in temperature within our reactor, we have to take into account. Hence, we have this equation here. This will be our third equation, and it basically takes into account the inlet temperature, the heat of our reaction, specific heat capacity of A, and also the reference temperature. We managed to derive catalytic weight in a form of conversion. We therefore then derived our pressure drop also in a form of conversion. Lastly, we derived the temperature with change within our system in a form of conversion as well. If we solve all these 3 equations together simultaneously, we will get the catalytic weight, the pressure, temperature, and the rate of our expression, or also the volume of our reactor. If you're asking yourself, where are we going to get all this information? All we have to do is look at stream number 14. Consider its flow rate, the inlet flow rate of the streams of FAO, FBO, FCO. Take into account the temperature that goes into stream number 14 and also the pressure that goes into stream number 14. With that being said, now we can substitute into equation number 1. We already know all our parameters. The only unknowns in this equation here, it's the weight of the catalyst, it's the pressure, and also conversion itself. We only know that it ranges between 0 and 1. If we substitute into our second equation here, we only have 2 unknowns, which is the catalytic weight and the pressure. Also, my apologies, the temperature, it's unknown as well. So everything else we can substitute. It should yield the second equation. Lastly, the third equation, we can just substitute. Everything is known. We know the inlet temperature, we know the specific heat capacity, and the reaction heat at the reference point. I used ODE to help me solve those 3 equations. I couldn't imagine myself trying to solve them by myself. They are so long, hence we have ODE, like octave. So for example, we are going to tell octave, for equation 1, these are our variables. For equation 2, these are our variables and their answers. Lastly, for equation 3, these are our variables If we go to the first equation on octave, we can write it in its simplicity. Don't get confused, guys. This is basically the equation that we're looking at in the form of catalytic weight. The second equation was the pressure drop. Don't get confused. It's just basically programming language expressing those equations in a way that octave can read them. And lastly, the temperature equation. If we solve both equation 1, 2, and 3 simultaneously, tell octave to display X, P, T, and W, you should get your results at different conversions. So octave will give you results in this format here, which basically this first line is all the temperatures, hence they're written on this table here at different conversions, 0, 2, 4, 6, 8, 10, expressed here. Also, different temperature changes within our reactor at different conversions, expressed here. Lastly, the catalytic weight, which remained constant inside of our reactor at 48.59. Now that we have that, we can move forward and calculate the volume of the catalyst for one tube. We can simply take the mass of the catalyst that was calculated using ODE, divide by the density to get our volume. In cubic meters, you can convert it to liters, it's 340.49 liters. Now, there's various ways to get the number of tubes. For this particular example, I just assumed there are 5 tubes within my reactor. And if I multiply this answer here by the number of tubes, I would get a total reactor volume of 11,917 liters. Okay, now let's look at option number 2. For option 2, we are going to look at this equation here. We know that rate law can be expressed in this equation here. If you make V subjective to formula, you can express it in this equation over here. So we have equation 1 and 2. We also know, or we saw above, that the rate law can be expressed in a form of catalyst. We are going to tell octave between 0 and 1 with a spacing of 0.2, find the different reaction rates at different conversions. Display your answer. For RA, it will give you your answer. Secondly, now that we have our RA at different conversions, we can get our V. So we simply took RA at the conversion of 0.2. You can do it for 0.4, 0.8, and 1, 100% conversion. Write this integral equation here in your programming language. Octave will therefore then give you your answer. At that particular rate, your volume ranges between 283 liters and 1.4 liters. Now, the third equation, the third option that one might want to consider. I got this one from literature. And it basically takes into account the length of the tube, also the diameter of the shell. So to calculate the number of tubes, we are basically going to take into account the diameter of the tube, which can be assumed to be 0.15 meters, the length of the tube, which can be assumed to be 4.88 using the Toller and Sinot textbook, and lastly the density of our catalyst given to be 1,200 kilograms per meter cubed. If you substitute everything, you should get the number of tubes within your reactor to be estimated 103 tubes. The shell diameter. We are going to take into account the diameter of the tube, also the number of tubes, and also this expression here, which is called the performance fraction. You can calculate it manually. I got mine to be 0.67. I found the diameter of my shell to be 1.86 meters. Now, lastly, let us get the volume of our reactor. So for the volume of our reactor, we are first going to get the total length of the reactor, which is approximately found to be by adding the length of the tubes and the diameter of the shell. If you add everything together, you get 6.74 meters. We can therefore now calculate the volume of our reactor. If we substitute everything, you should get at least 10,752 liters. By looking at everything here, for option 2, we got the smallest reactor volume at only 1,412 liters versus option 1, which gave us 11,000 liters, and option 2, which gave us 10,000 liters. One might want to really look into the second equation and see where did we go wrong. But overall, yes, there's really many ways, guys, to calculate the volume of your reactor. I really hope this information can be helpful in terms of calculating your volume of your reactor. Don't forget to also do your own research by looking at different textbooks such as reactor design textbooks or plant design textbooks that can really help you to calculate all this information that you might need when you're sizing your own reactor. There's a lot that goes into the reactor, guys. We could have also simply used Aspen to size our reactor, and it could have showed us at different conversions the different lengths within our reactor, and also given us the residence time, which could have also helped us to calculate the volume of our reactor. So there's really that goes on to these things, guys. I was just showing you guys how I would go about it. Thank you so much for watching. Till next time, bye. Let us look at this refrigeration cycle here using carbon dioxide to cool off water. I'll be using Aspen Hysis. Prior to this, I've done actually a fun activity or a fun example using cocoa simulation. So I figured out why not also show you with a different simulation as well. So the first step here will be to use or to log onto your Aspen simulation. Once you've logged in, you'll then proceed to go under component specification and add all your components. In this scenario, you only need carbon monoxide and water. Once you've added both these components, the next step will be to go to methods. Under methods, we are going to specify the base method as Pang-Robinson. After this step, now on Aspen simulation, we are just going to be clicking next, next, next until all our required properties have been calculated. My results are now available and all the tables that were required by Aspen have been generated. The next step now is to proceed and go to simulation. Under simulation, this is where now we're going to try and draft our refrigeration cycle flow diagram. Okay, let's start. At my equipment, I'll be starting with my compressor. Let's include a valve. We are going to add a heat exchanger that's going to act as a condenser. The heat exchanger whereby heat will be transferred between carbon dioxide and water. Let's try and connect the streams. Okay, it looks like I have to rotate my compressor. So I'll be rotating it on my vertical axis. I'll be connecting my streams from the compressor to our condenser, from the condenser to our expansion valve, from the expansion valve to our heat exchanger, from the heat exchanger back to the compressor. Also, let's connect the water inlet stream and the water outlet stream. Next step is just to label everything. So the first point will be the stream that's exiting the valve. So this will be stream number 1, carbon dioxide. Stream 2 will be the one that exits the heat exchanger. Stream 3 will be the stream from the compressor to the condenser. And stream 4 will be the stream from the heat exchanger to the valve. Also label our equipment accordingly. So we're going to have a heat exchanger, compressor, condenser, and expansion valve. The next step now is to specify some few components. Let's start with our compressor. For our compressor, we are going to say we want it to be isentropic, and our discharge pressure will be 60 bar. So we expect stream 3 to be 60 bar. For the heat exchanger, we are going to specify our outlet temperature to be 22 degrees Celsius at 60 bar still. For our valve, let us specify the outlet pressure. And we are going to say we expect the pressure of 60 bar. And we are going to say we expect the pressure of roughly at least 27 bar. Now, let us specify the inlet streams. We only have to specify 2. So I'll specify the inlet stream of the refrigeration cycle whereby carbon dioxide will be running, and that's stream number 1. In terms of mass, I will say I'm expecting 1 more percent or 100% of carbon dioxide and 0 water. Specify the flow rate within the stream, and the conditions. We can say we expect the stream to be minus 9 degrees Celsius and 27 bar. Stream 6 as well. In fact, let's label it to H2O entering, where we need to cool. So we're expecting to feed in a warm water flow rate and expecting it to come off as a cool water flow rate. Okay, so for our inlet water stream, we can specify that we'll be feeding 12 degrees Celsius at 1 bar, also in a form of mass. We can specify the mass flow rate to be roughly just higher than that of carbon monoxide. Okay, we've specified most of the parameters. The only thing that's short in here is the heat exchanger. For our heat exchanger, this carbon dioxide is entering at minus 9 degrees Celsius and water is entering at 12. That means the carbon monoxide stream is the cold stream. It still says we are not done yet, and that's because we need to specify the specifications. If you're not sure, always click next and it will guide you on what is shorting. So I'll specify that the temperature here is -1 degree Celsius. Now that we've computed everything, oh, it cannot determine which stream is inlet is hot, and okay, let's fix that. So I'm just gonna reconnect destination. It's still saying no. Perfect. Now the inlet streams are perfectly aligned. So I'm just gonna click next so it can guide us. What are we shorting with? Okay, so water. So it says we didn't specify the water stream. We did specify the temperatures, but not the components. So we only have 100% water and 0 carbon dioxide in the stream. Once satisfied and happy, now we can run our file. It says that while checking input specification, there was an inconsistency of water settings detected for 2 streams. Something to look into, definitely. Okay, so now I can actually go to my simulation and just look at our streams. Let us go to modify and just select some few parameters there, temperature, pressure, and the mass flow rate. It's solved nicely. I just need to look into this warning here. Stream 1 goes into our heat exchanger at minus 9 degrees Celsius, exchanges heat with the inlet water stream, and exits at minus 1 degrees Celsius. The carbon monoxide stream that was used to exchange heat then gains energy or heat rather and goes to 22 degrees Celsius. The pressure here remains constant from the expansion valve all the way to stream number 2 after the heat exchanger. So our compressor here will be used to increase the pressure from 27 bar to 60 bar. Once it travels here, the temperature has increased due to the compression that occurred and the condensate, rather, that's why we have it here to help us reduce the temperature. By using a cooling effect, the temperature will reduce from 100 degrees Celsius to 22 degrees Celsius. After it goes through an expansion valve, both the pressure and temperature will change. The temperature will drop to minus 9 and the pressure will go to 27 bars while it also dropped. The cycle then will definitely continue. So this process here is known as a refrigerant cycle, and it is used in most processes such as air conditioners, your refrigeration at home. It is a very, very complex process that's used in the industry. The reason why we have this refrigeration cycle here, this process here, was simply just to reduce the water from 12 degrees Celsius to minus 1 using a closed cycle. This carbon dioxide here will continuously continue to flow throughout the system from 0.3 to 0.4, 1, 2, just like that, as the water continuously the temperature cools off to minus 1 degree Celsius. So yes, guys, that's it. I really hope this makes sense. We also have the exact same example using a different software. This time around, we used Cocoa Simulation. I'll also try this example for you guys as well using DWSim to cater everyone's needs because we all prefer different simulators. Okay, now till next time. Bye. Let us look at this beautiful example over here, whereby we are carbonylizing DME to form methyl acetate. This is how I would go about when it comes to the approach of forming methyl acetate from reacting carbon monoxide and DME. By the way, if you want full information on this particular example that we're looking into here, just go down the description box below, whereby it will take you to our website. You can download the files themselves, including the simulation, and you can run it on your laptop or any simulation of your choice. This includes DWSim, Coco. Look, we've got you. Okay, now that I've taken that out of the way, let us look at this example as it is as a whole, not focusing on the details of it. It's just a summary of what is happening. If you want to react carbon monoxide, DME to form methyl acetate, this is how I would go about it. You can have an alternative one. Let me know if it also works. Okay, so the first step would be to have a carbon monoxide stream and a DME stream with different compositions. For example, carbon monoxide can exist at 98% with a small fraction of hydrogen, and for DME we can have it at 99%, almost 100% conversion, and a small fraction of methanol. The next step will be to compress our carbon monoxide. Why is that? So here, carbon monoxide is fed at ambient conditions, including a very low pressure, not so low, but 5 atm. And if you want to increase the pressure, you can use what we call a compressor, which uses a very interesting mechanism. It simply reduces the volume in order to increase the pressure. So why not use it, right? So yes, so I will feed my carbon monoxide and DME into mixer 1. After mixing together, we will have a small portion of methyl acetate starting or beginning to form, and a small fraction of water that might be found also within that stream. Okay, now we can react everything. Because the reaction is exothermic, temperatures are highly expected to increase above 100 degrees Celsius, close to 255. For example, after reacting there, I used the Gibbs reactor. We can now go to the distillation column, where we are going to be separating everything that we don't want from our methyl acetate. At the bottom, we can tell Aspen we want to achieve 100% conversion of methyl acetate, and the top stream can be the remainder of whatever molecules that were found or present at that stage. So we'll find that at the top stream, a small portion of carbon monoxide might exist at 28% and DME existing at 78%. Now, we are engineers. We do not waste anything. We always recycle back to the system. Hence, we took it back to the system. We used a heat exchanger there because at high temperatures, you'll find that carbon monoxide and DME will flow super fast. So in order to mitigate that, let's include a heat exchanger and control some parameters so that we continuously maintain a constant flow throughout our simulation. Now, in order to feed this back into our system, let's use a mixer. It only made sense to mix from the carbon monoxide stream. If you want to, try and mix from the DME stream and let me know how that goes. So yes, after connecting the mixing stream, it will go back into the system and everything will be a continuous flow. There could be different scenarios. For example, you could have been given a problem that says design a plant that produces methyl acetate for 330 days and you want to achieve 600,000 metric tons. So hence you'll convert everything and end up getting to 122. Yes, so if you're interested in more information, click on the link below and it will take you to our website. But for now, that was just a summary. Good luck. I hope this helps you somewhere, somehow. You've got this. Let me know if you need anything else. Here we solve all kinds of simulations. There's absolutely no simulation that's hard to solve as long as you understand the principles and the chemical formulas themselves. Till next time, bye. Let us look at this process here, which is known as carbonylation of dimethyl ether. We simply are going to be reacting dimethyl ether DME with carbon monoxide to produce methyl acetate. Now, on this process simulation that you're looking at here, we will be going and doing step by step of each process. It's a very short process and might need to be modified if you want to, but this is how I would go about it if I was asked to create such a process. So the first step is to react dimethyl ether and carbon monoxide at ambient conditions. At these conditions, our DME is liquid, but our carbon monoxide is in its gas phase. So if you wanted to react this two at gas phase, you can just change the condition of DME, just aligning it with its gas phase, just aligning it with its phase change diagram, just to know that which parameters it becomes gas phase. But I decided to go along and just react this two at ambient conditions. So my DME is liquid and my carbon dioxide it's a gas. So I will be mixing these two together. After they mix together, the conditions of the temperatures didn't change much. As you can see there, my pressure is still 5 bar and my my temperature is 20 degrees Celsius. Now the next step, to favor our reaction, we are going to increase the temperature. So I'm going to use there a heat exchanger. This heat exchanger here will simply be increasing the temperature from 23 degrees Celsius to 50 degrees Celsius, and at 20 bar. As you can see that the mass balances, the stream that's going in, the inlet stream and the outlet stream, are equal. Now the next step will be to go to our reactor, the Gibbs reactor. For the Gibbs reactor, we are going to simply react our carbon monoxide and DME in order to produce methyl acetate. This process is known as carbonylation of DME, because we are reacting DME with carbon monoxide. After these two react together, they will move to a separator, whereby they will be separated into 100% of methyl acetate and the remaining components, which is DME and carbon monoxide. This too can be recycled back into the stream there. Due to my mass not balancing, I introduced a splitter just to purge just some few amounts of some products there and recycled back the wanted byproducts into the system using mixer 2. Now let's look at our equipment per individual. The first equipment here that was used was a mixer, and my mixer will be mixing at very low pressures here. If you wanted to, you could have specified your own desired pressure. Another equipment that we can look at here, it's the heat exchanger. For this heat exchanger, I only specified the flash type for it to be temperature and the pressure here. So the outlet temperature that is expected, it's 50 degrees Celsius, and the outlet pressure that we expect from this heat exchange will be 20 bar. Because we are using a Gibbs reactor, with Aspen you are not expected to specify the reaction type that will be taking place here, but if you had to, you would just simply specify that 1 mole of carbon monoxide reacts with 1 mole of DME to produce 1 mole of methyl acetate. But yes, for the Gibbs reactor, we are simply going to specify the temperature to be 100 degrees and our pressure there at 20 bar. So we are simply telling Gibbs reactor at which conditions our reaction will be taking place. Another equipment that we can look at here, it's the separator. For the separator, all we have to do is specify one of our outlet streams. I chose to make the bottom stream, which is MA, to be 100% of methyl acetate. Another equipment we can look at here, it's the splitter, split 1. Now for the splitter, it allows you to specify some few parameters. I chose to go with the split fraction, and for stream 4 we will be separating, or we want a fraction of 0.9 compared to that of stream 5. So this means from 1 or 100% mole fraction, we want 90% to go to stream 4 and the remaining 10 to go to stream 5. This, I simply included it to help with my mass balance, but of course we still have our unwanted products in our stream 5 that might have to be recycled back into the system. So if you are considering following this procedure, you might want to amend some few things to cater it to meet specific engineering sense, in sense that as engineers we do not waste anything. We always make sure we reuse, recycle and make use of every product.